Hi, this is our 25th lecture, and I want to start off with today is an opportunity for anybody who has any questions to ask any questions that they'd like to. We've recently got our homework forward, and I don't know if anybody's had a chance to look at it. Of course, from what I handed to people that were in class on Wednesday, I added a problem to that, and I sent that out through email, the new assignment, or the edited correct assignment. And I also posted it on Blackboard too, so you got it as an attachment, posted on Blackboard. And what I'd like to ask is if anybody has any questions about anything. I'd like to see, maybe you haven't had a chance to look at it very well yet, but anybody want to ask anything about the homework or about anything else that we've covered? Okay. Well, if there's nothing, no questions, then I'm going to move on to a different topic within the course. That's about limits of functions. Anybody want to ask anything? Well, before I move to that, let me tell you that in that last problem that I gave out, it was to show that something is a Cauchy sequence. What I'd like for you to do is do it analogously to what we did to show that 1 over n was a Cauchy sequence. Okay, something like that. Matter of fact, it could involve the fact that 1 over n is a Cauchy sequence. That'd be kind of nice to use that. Okay, well, with that being said, let's start off. We're going to talk about limits of functions. This is chapter 4 of our text. It has to do with function limits. Taking limits of functions is something that you could have seen in calculus. Some people emphasize this more strongly than others. I'm a person who happens to, when I teach calculus, to emphasize function limits. But essentially, we want to know if the output values for a function get close to something as the input values get close to a particular number. So that's what function limits is asking. But the first question really is, what kind of number can we let input values get close to when we talk about function limits? So could we just let x go to any number, x being the input value, go to any number? Is that okay? For any function? The answer is no. So we start off by saying, well, what is it that we're going to be talking about where we're going to let x go towards the function? So here, a definition. We're going to say that a cluster point, so what we're going to give is given a set A is a subset of R. The number C is a cluster point in A, or cluster point, I can say the right thing, cluster point of A, if for each delta greater than 0, there exists an x that is an element of A with x being different than C, and the distance between x and C is less than delta. That's the definition. What does that mean? What that means is that a point C is a cluster point for a given set A, it's a subset of R. If no matter what distance you give me, that's delta, there exists something from A, point from A, that's the x, that's different from C, but yet the distance between x and C is less than the number you gave me, the positive number you gave me. So that means that C is a cluster point of A, means you can get arbitrarily close to C with points from A, where the points from A that you're picking are different than C. Let's write that down, and then let's look at some examples. So the idea is C is a cluster point of A. If A different from C that are arbitrarily close to C. Let's look at an example. Here, I'm going to let A be this set. I'm going to let it be the set 1 over n, n running from 1 to infinity, union plus, let's say, 3 to 5. And so I want to ask some questions about whether something is a cluster point of the set A or not. Okay. Graphically, of course, here's what it looks like. Here's 0, it's not in the set. Here's 1, that's in the set. A half is in the set, because that's when n is 2. A third is in the set, that's when n is 3, and so forth. And then we got the region here, 3 to 5, where we have everything in between 3 and 5, and we include 3 but not 5. Dots in here that come from the 1 over n. And here's the first question I want to ask you. Is 5 a cluster point of A? Okay. What does it mean to be a cluster point? It means that it's a number such that no matter what distance you give me about that number, no matter what delta you give me about that number, I can find something from A within that distance of 5 in this case that's in A but not equal to 5. So look, if I give you some little region, this was 3, this was 5. If I give you this little region about 5, is there something in A is there something in A that's not 5 that's in that region? Yes. No matter what little region do I put around 5, is it going to have things from A in it that are different from 5? Yes. The answer is yes. Let's do some more. One thing I want you to know is I said 5 was a cluster point of A, but let me also note here what's kind of a interesting aspect of 5 for this example A. But 5 is not an element of A. So you can be a cluster point of the set without being in the set. Is 3 an element of A? I'm not an element, but a cluster point. What is the question asking? The question is asking me, are there points from A different from 3 that are arbitrarily close to 3? Dalvin's saying yes. If you look at our set A again, if you put any region about 3, any delta region about 3, does it have points from A that aren't 3? Sure will. Every little region I put about 3. So the answer here is yes. And one thing I'll tell you is 3 is an element of A. So you could be a cluster point and not be in the set, and you could be a cluster point and be in the set. Let me ask this question. Is 0 a cluster point of A? What do you think? Here's 0. Is 0 a cluster point? When I put some little region about 0, no matter what little region I put about 0, will it always contain things from A that aren't 0? Chuck's saying yes. Audra's saying yes. Other people maybe still thinking about it. Audra, if you said yes. Chuck, if you said yes. What points could I get that are arbitrarily close to 0? Where are they coming from in that? Remember, A is 1 over n plus the numbers in between 3 and 5, including 3 but not 5. How do you get those points? Where are they coming from? What part of A are they coming from? They're coming from the 1 over A. So no matter what little region I put around 0, is there going to be guys from A in here? And the answer is yes, because 1 over n converges to 0. So no matter what delta, the delta is like your epsilon in the definition of convergence for 1 over n. You're going to find things from the sequence 1 over n, which is contained in A, that are within that delta units of 0. Is that okay? So the answer here is yes. Everything's a cluster point. Let me ask you this question. Is 2 a cluster point? So here's 2's right here. Is it the case that no matter what region I put about 2, there's something in A that's within that region, 2, but is it 2? No. Then if I look at half a unit about 2, go to 1.5 up to 2.5, there's nothing from A in there. So here, 2 was not a cluster point, and 2 wasn't in the set. What about this question? Is 1 a cluster point? Go back. 1 is in A itself. When n was 1, we got out 1. That was given an answer. He said no. If you look just at the region, it's a quarter of a unit to the right of 1 and to the left of 1, and you say, is there something in that little region about 1? Is there something in that little region about 1 from A that is not 1? And the answer is no. So that's very interesting, Dowdy. That's very interesting because I'm saying here that I can produce something in A, because 1 is in A, but it's not a cluster point. So there doesn't seem to be a relationship between A and whether you're a cluster point. Remember the idea for cluster point was that you're a cluster point for a set if you can get points from that set different from the cluster point, respective cluster point, that are arbitrarily close to that respective cluster point. Is that okay what I've written? Well, there is a fact that tells you whether something's a cluster point or not, besides the definition. So there's an if and only if statement. You don't know what that means. So here's the theorem. It says bar. It says a number C, this element bar, is a cluster point of a subset of a set A that's a subset of R. If and only if there exists a sequence I'll say x sub n, and run from 1 to infinity, that's contained in A, such that the limit as n goes to infinity of x sub n equals to C, and x sub n is different from C for all n element natural numbers. Just to have up here, I'm going to write on the sideboard what the definition of the cluster point was, so give me a minute while you're writing it down. Here was the definition of the cluster point. So given subset bar on A, C, an element bar is a cluster point. If for each delta greater than 0, there exists an X element of A with x being different from c and that's the value of x minus c less than delta. Okay, so that's what we're going to use, that definition of cluster points in the balance in this proof of this theory. Well, I'm ready to start on this proof. So here I'm going to let C be an element of R and A be a subset of R. Now, we're having an if and only if statement, so to prove this direction, we're going to let C be a cluster point of A. What is it that we got to prove? We got to show there's some sequence from A whose terms are all different from C, but that sequence converges to C. That's what I got to produce. I got to produce this sequence for this direction of the proof. So, how do I produce this sequence? Well, here's what I do. Consider deltas equal to 1 over n. So I'm thinking of a bunch of deltas. So it's delta sub n equal to 1 over n. For each particular n, that's a positive number. Since C is a cluster point, okay, I'm giving you a delta, 1 over n, okay? Then there exists, I'll say, an x of n, this particular term, is in A, such that x of n is different from C, because that's what it means to be a cluster point. I can find something that's different from C in A, with the distance between x of n minus c being less than delta, which I'm saying is 1 over n. Okay. So for each natural number, n element of n, we have x of n element of A with x of n different from C and the absolute value of x of n minus C is less than 1 over n. So for each n we're going to find one of these x of n's. So that means we have formed a sequence. For x of 1, for n equal 1 I got x of 1. For n equal 2 I got x of 2. It satisfies what's here. Okay? And what do I know about each term of the sequence? So thus we have a sequence. So what do I know about the sequence? Well, first of all, each term of the sequence is in A. So that means as a set, this sequence is a subset of A. So we got a sequence from A. Okay? And we know for each term of the sequence is different than C. Different than C. And that's true for all n element natural numbers. Well, that's two of the qualities that we wanted to come up with for a sequence that we're trying to create. There's one more quality it has to have. It has to converge to C, Dalvin said accurately. That's right. Now, here's what I want to tell you. Since x of n minus C is less than 1 over n, I'm writing very small here, but then that means the limit as n goes to infinity, that forces the limit as n goes to infinity, of x of n to be equal to C. That's what it does. And that's this part of the proof. Okay, I'm going to stop for a second. It's that last part I'm going to explain a little bit. It's based on the fact that we did. Okay, this last part. We did a fact a good while ago, so I'm not going to give you the idea, I'm just going to state the fact. We stated the fact that was the following. And here's the definition. I'm going to go over here and tell you what fact we're using for this lesson. It says, a fact that we proved earlier was that if x of n is a sequence and a sub n is a sequence of positive numbers, with the limit and then going to infinity of a sub n equaling 0, and if there exists an m element of natural numbers such that for all n bigger than or equal to m, absolute value of x sub n minus x is less than c times a sub n for c being positive, then the limit as it goes to infinity of x sub n had to be equal to x. It's a fact that we proved long ago. Long ago. I'm even going to tell you where it is in your book. It's theorem 3.10 or something like that. Let me see if I can find it. It's on the left-hand side of the page. Come on. Let's see if I can find it. I'm looking at it. It's theorem. It's on page 60 of the book. Okay, that's what it is. It's theorem 3.1.10. Okay? We proved it. And we're using it. We're using that fact right here. Let me show you. Look, this is my a sub n, 1 over n. It's a sequence that goes towards 0, and all of its terms are positive. And this quantity right here is less than 1 over n. The c that's involved in my theorem is 1. Positive number. 1 times 1 over n. That's what it is. And this statement is true for all n. So you say m equal to 1. Right? 1. And because this guy goes to 0, it forces these guys to get arbitrarily close to each other. That means x sub n is going towards c. That's the idea. Well, that's only half the proof. Well, we've got to go the other direction. So for the other direction, here we're going to say, suppose there exists an x sub n, it's a sequence. It's contained in A with x sub n being different from c for all n element natural numbers, and the limit as n goes to infinity of x sub n equals to c. We want to show that c is a cluster point of that. That's what we want to show. How am I going to show C is a cluster point of A? I'm going to use the definition of a cluster. That's all I got. And so I'm going to use what's over here for the definition, the criteria that's needed. Let me give everybody a second right now. Yes, sir.
You might have said this before I walked in, but when we say that the sequence is contained in A, does that mean that all of the terms are in that set?
Yes, sir. That's what it means, but I didn't say that before. I don't think. That is what it's meant. Yes. So we're thinking of them as sets. Okay. And so each item in this set is an item in this, each element. That's what we're thinking Yes, sir.
Thank you.
Thank you for asking. It's a good thing to get clarified. Okay. So how do I show C as a cluster point value? Well, I use this definition, so what does it say? It says, well, anytime you give me a positive delta, I'm going to give you one. I don't know what it is, but it's positive. But what do we need? We need an X element of A with X to be different than C and the distance between X and C to be less than delta. That's what I need. I need to produce something in A that's within delta units of C that's different than C. That's what I got to do. Okay. Well, since X sub n is a sequence in A with X sub n being different from C for all n element of natural numbers, and this is the part that I'm going to concentrate on right now, and the limit as n goes to infinity of X sub n equals to C. So that's the part I'm going to concentrate on. Look, I know the limit as n goes to infinity of X sub n equals to C. I've been given a positive number, delta. But delta is like the epsilon for the definition of a convergent sequence. So I've given you this positive number. I know this sequence converges. What does that mean? That means there exists a K. There exists a K element of natural numbers such that for all n bigger than or equal to K, what happens?
Absolute value of X sub n minus C is less than delta.
That's what I'm going to have. Yes. That's exactly what I'm going to have. Except for all n bigger than or equal to K, X sub n minus C is less than delta. So in particular, X sub K, that particular K, whatever it is, X sub K, it's going to be an element of A, and because it's part of the sequence, it's different from C, and X sub K minus C is less than delta. Look, I was trying to produce some guy in A that's within delta units of C. It wouldn't equal to C. I just did. It's X sub K. That particular guy. So that means that C is the cluster point. Okay. And that concludes the proof. The reason we're going over cluster points is because we wanted to talk about limits of functions. And what we needed to know is what can the x value be, the input value, what can the a value be, or c value be, that the input values get very close to be part of a limit of a function. And so what we're going to discover is that we're only going to be talking about taking limits of functions at cluster points to their domain. So I'm ready to write down what the definition of a limit of a function is. The setup is, we would say, let A be a subset of R, which we suppose, or I'll say let F, I don't know how well I've described this notation. Let F go from AR be a function. Okay, what do we mean by F goes from A to R? The domain of F is A. That's what we mean. So F grabs things from A and yields out a real number. And A is a subset of R. Okay. Let C be a cluster point of A. Then we say F has limit L at C, and denote this by the limit as x goes to C of F of x equals L if for each epsilon greater than 0, there exists a delta bigger than 0, such that for all x in the domain of F, that's A, with 0 less than x minus C is less than delta, then the absolute value of f of x minus L will be less than epsilon. Man, that's a long definition. Let's incorporate a lot of ideas. Well, it does. Give everybody a second to think about that. Okay. Now I want to show what this, I want to write down what this means. I want to show kind of a pictorial representation of this. Just a minute. I am a little sick and have not been sleeping enough. So I've been making mistakes left and right. And one of the mistakes I made, I think you can relate, or you'd understand what the mistake is, not you relate to it, you understand what the mistake is. So one of my advisees has come to see me. He said, well, I'm going to get my schedule ready for the fall term. I said, okay, let's go ahead and look together. So we were looking, and I said, I want you to take Math 2500, statistics. He said, well, okay, great. Well, we already had him listed for taking Cal 2, okay? And so we wanted to make sure that the statistics class wasn't offered at a conflicting time with Cal 2, so I'm looking it up. When I looked up when statistics was offered, I looked at it. It looked very strange. When I looked at what days it looked like it was Monday when I read it. Monday, Tuesday, Thursday. Now think of your schedules. We never have classes, especially for the math department, on Monday, Tuesday, Thursday. You have a Tuesday, Thursday class, and Monday, Wednesday, Friday classes. You might have one day a week class. But 3 days were there Monday, Tuesday, Thursday. And plus I looked at the hours. And on Tuesdays and Thursdays, it was the time, or each of them these days that I thought was one of the schedule. It was from 2 to 3:15. If you add up those hours, it's much more than 3 hours a week. 2.5 hours. What's supposed to be. Much more. You know, 2 of those days would suffice. But it's saying I'm looking at MTR. That's when they list. So I'll go to see our department secretary, Mrs. Thacker. I said, when is this Math 2500 offered? She said, Tuesdays and Thursdays from 2 to 3:15. I said, okay. I said, do you mind going to our course listings? You know, everybody sees at the website. She said, sure. I said, can you scroll down to Math 2500? She does. I said, can you tell me what days it's offered? She just looks at me with her mouth open. She said, John, it's offered on Tuesdays and Thursdays. And I walk up behind her and I said, look at that M right there. She said, that M is the first initial. It's the initial of the first name of the person teaching the class. Mitra Devkota. And that's how tired I was, that I thought that M meant Monday. And that's what happened. I was embarrassed. I also did something else kind of worse about misreading something. And Mrs. Thacker was also involved with that. And so she said to me after this, she said, I'm worried about you. I'll catch up with stuff. All right, what's the idea? You can go look. You look on the schedule. That one kind of looks like it should be part of the schedule. You do. You go look if you want to.
I'll take my word for it.
Ideas. The limit as x goes to c of f of x equals L means the output values of f of x can be made arbitrarily close to L for all x except c, except possibly c. That are arbitrarily close to C. Got what? That's the idea. Well, I mean, output values f of x can be made arbitrarily close to L. That's the distance between f of x and L is less than epsilon. Epsilon is any arbitrary distance. When does that happen? That happens for all x in the domain. I should have said in the domain. For all x in the domain of f, such that x, the absolute value of x minus c, is less than delta. So you're being arbitrarily close to c. But I've got this except possibly c. Why is it that we don't worry about c? Where's that in the definition? And so I'm going to point to it. The part of the definition that says you don't have to worry about what happens at x equals c is this part. You see, we say that the absolute value of x minus c has to be greater than 0. If x were equal to c, c minus c is 0. The absolute value of 0 is 0. That's not bigger than 0. So we're not allowing x to be equal to c. So that's why we have this idea being captured that we want to be really close, or to make the output values be really close to L within epsilon distance. We can do that as long as we let the x values be really close to c within delta units. For any x values really close to c within delta units, for any of them except for c itself. We don't worry about c itself. Okay? In terms of a pictorial representation, let me draw it right here. Here's kind of what it looks like. Let's say that's C. That's L. Here's my function. Okay, here's what's happening. Look, you think that the limit as x goes to C is L. What we think? We're thinking that the output values for f of x are really close to L when we're really close to C. Except we don't care what happens at C itself. At C, maybe it's up here, this point is F of C, the y-back is. What is happening is, as long as the limit is x goes to C of f of x equal to L, it means that no matter what distance I put about L, epsilon above or epsilon below, if you want the output values to be in this band, what you got to do is you got to be in this band of about C. So this is my delta units about C that I would pick. Does that make sense? And everything in here is sent to something that's in this band of L, except maybe right at C. F of C is not in that band, but we don't care what happens at C when we're talking about a limit. Here, the limit as x goes to C of f of x equals L. Is that okay? That's the idea. That's the pictorial representation. It's pictorial what we did. Okay, Does anybody have any questions about it? Well, it's good to prove something. An example. So let me do an example. The limit, if x goes to, let's say, -3, 2x plus 9, let's make it 10, equals to 4. I'm going to prove this. How do we prove it? All right, that's the first thing. So we're using the definition. The definition has a requirement that no matter what positive number is given to you, we can find something. And when we were looking for sequences, when we were working with sequences, we needed to find, and that's only given, we need to find a k. Here we're not looking for k. We're looking for a, what's the definition say? A delta. That's what it is. We want to find a delta. We need a delta. Greater than 0, such that for all x element of the domain, which we're calling A, with 0 less than absolute value of x minus c be less than delta, then absolute value of f of x minus L will be less than epsilon. That's the generic definition. I'm going to rewrite that sentence with the specifics of the problem we're talking about. Just a second. You can look it up. I'm telling you, online. If you go look at the class schedule, you're going to see that M down there, and you're going to say, you look, Melissa? It's there.
The M's there, but it's not close enough to be.
Oh, it depends on how bad your eyesight is. Yeah, it's there. That's why Monday, Tuesday, and Thursday. Okay, so specifically, we need a delta greater than 0, such that for all x, well, wait just a second. You know, what is my function we're talking about? We're talking about f of x. You know, I'm right here to the side. Remember what we're looking at? The generic form is limit as x goes to c of f of x equals to L. Look, I'm going to say something encouraging. When I say this, I mean it to be encouraging, not something insulting. This, to me, is a matching game like it's on Sesame Street. Okay? What's f of x? Up here, what's f of x in our particular problem? 2x plus 10. I'm going to write down what a is. So I'm thinking, what's the domain for the function that's 2x plus 10? Now, we never really consider that in this class, but what's the domain of that linear function? All real numbers. With 0 less than absolute value of x minus c. What's c? It's a matching game again. It is delta. Minus 3. Very good. Less than delta. Then, it says absolute value of f of x. What's f of x? It's 2x plus 10. Minus L. What's L? Our problem. 4 will be less than epsilon. That's what I want. That's what I want. So I'm going to concentrate on that f of x minus L part to be less than epsilon. That's what I want to have happen. So we want the 2x, it says plus 10 minus 4 to be less than epsilon. That's what I want. I'm going to simplify what we want. We want 2x plus 6 to be less than epsilon. That's what I want to have happen. The only thing I get to control is how close x is to minus 3. How close x is to minus 3. I get to control the absolute value of x plus 3. That's what I get to control. Okay? That's what I get to control. Well, wait a minute. Looks like I can get x plus 3 inside absolute values out of this statement. I can relate what we want to what I can control, which is the absolute value of x plus 3. I get to pick the delta. Okay? So here, that means we want 2 times the absolute value of x plus 3 to be less than epsilon. What does that mean? I want x plus 3 to be less than epsilon over 2. But it's the absolute value of x plus 3. I'm pointing to it over here. It's the absolute value of x plus 3 that I get to control. I get to pick the delta. So that if we get within a certain region of, we get x plus 3 inside absolute values less than a delta, we get what we want. Wait a minute. The delta's staring at me. What should I let delta be, John?
Epsilon over 2.
And you know how when we did proofs before having to do with sequences, I said you don't have to work backwards? Well, you don't. Okay? Here, either. That's the delta we're looking for? That works. But if you wanted to be formal about it, if you said, so, for all x element of R with 0 less than x minus a minus 3 less than epsilon over 2, that's my delta, then what would we have? So what I'd have is I multiply everything by 2, so that 2 is in times absolute value of x minus, or x plus 3, will be less than epsilon. You can bring the 2 inside the absolute values here, and you get, which implies that 2x plus 6 inside absolute values is less than epsilon, implying that, well, I can rewrite this as 2x plus 10 minus 4, that's what 2x plus 6 is, will be less than epsilon. And that's true, remember when it's true for all x in R, with 0 being less than x, the absolute value of x minus 3, less than epsilon over 2. So that tells me that the limit as x goes to minus 3 of 2x plus 10 equals to 4. I draw the picture here. 2x plus 10. Let's look what's happening at minus 1, 2, 3. And minus 3, if I just stick that in the function, I'm going to get out 4. There it is. If I were to stick in into the function 2x plus 10, if I were to stick in minus 2, I would get out, I think, 6. It's going up 2 units every time. It's looking like this. And what's being said is, if you want to be within epsilon units of 4, what you got to do is you got to be within epsilon over 2 units about minus 3. That's what it's saying. You got to be really close. You got to be half as close, half the distance away from minus 3 as you want to be about 4. You do that, and everything works. If you're within this unit of minus 3, you're going to be within this unit of 4. That's what this is saying. That's what it's saying. Check it out. What if we, I'm about to check. What if we said we let epsilon be equal to 1? So that means I want my output values to be within 1 unit. The output values for the function to be 1 unit of 4. I want the output values to be within 1 unit of 4. That means they could run up to 5 output values, or they could be down at 3. So here, I'm telling you, if you want to keep this function's values between 5 and 3, what you got to do is take the input values to be within half a unit of minus 3. Does that make sense? So as long as you're between minus 3.5 to half a unit, so I went that way, to minus 2.5, it would force these output values to be within 1 unit of 4. Check it out. What if x was minus 3.5? What's 2 times minus 3.5? It's minus 7. Minus 7 plus 10 is 3. That's the bottom number. Well, of course it is. Is that okay? In my picture. That's what it is. So if you're if you're down here to minus 3.5, you're still within 1 unit. So just if you're within that, minus 3.5 to minus 2.5, you're going to be within 1 unit, okay, of 4 with output values. Is that okay with everybody? Okay. Well, we look at it a little bit more if we need to. No problems. That's enough for today.